So thanks everybody for joining us today. We'll go ahead and get started. I'm really excited to introduce Greg Law. He's joining us here from Cambridge, where he's the CEO and co-founder of Undo Software, which does some reversible debugging, some other interesting stuff. So he's going to talk to us a little bit about that today, both the technical side and I guess some of the experiences of actually trying to build and run a company around this. So I'll let him take it away from there.
Yeah, thanks, Mark. Hey, so so I'm just going to run through an overview of what we've done, some demos, and I know that a lot of people in the room are kind of familiar with the concepts. So a lot of it, like explaining, some of it, like my standard pitch is a bit about why it's important, and I'll try to go a little bit quicker over that stuff because I think most of you kind of are already. I think I'm preaching to the choir on a lot of that. But maybe it'd be useful to kind of get a sense of how I describe this to customers as well. So there's that kind of side to it. With that, I'll flip. So this chap, I can just about see there, it's a bit washed out. A guy called Maurice Wilks, who I reckon has as good a claim as anybody to having been the world's first programmer, right? Because he was the first person to write code on a general purpose machine that did something other than just prove the experimental machine they were building worked, right? It was actually doing a real thing. And he says in his memoirs, this I think most of you read ahead, and this notion that I think most of us will be familiar with, right? Most people who've spent any time programming kind of realize fairly early on, it turns out it's really hard. And actually, so this was like in the 1940s. My daughter started programming in Scratch a little while ago, and she said, Dad, it's a lot of fun, but I have to do it a lot of times to get it to work. Which was kind of nice because now she could understand a little bit about what this company with the funny name that Dad started does. But so what was true then in the 40s is just as true now. And actually, it's getting. The problem is getting much bigger, right? Because computers are getting way more complicated. We're now running billions of instructions every second. Often we're looking for the one bad instruction in that billion instructions every second. So it's like the ultimate needle in a haystack challenge. It's kind of surprising we can ever fix anything if you think about it in those terms. And of course now everything's talking to everything else as well, right? And we're actually moving into a world that's becoming less sort of deterministic in terms of the software, right? So with machine learning and all these kind of things and just self-driving cars, so the world just becoming more and more uncertain as far as software is concerned, and understanding what's happened is becoming ever more important. So what we've done is develop this technology. It's kind of like, we describe it sometimes as like CCTV for code. Right? So trying to understand why software has gone wrong. Maybe even the software hasn't gone wrong, actually. Maybe you're just trying to understand like what happened. An example would be the flash crash that happened a few years ago, right? Now, this is with algorithmic trading, all kind of some weird stuff happened and the stock market went down by 20% in a minute and came straight back up again. And actually it happens all the time now. It's not a thing anymore, it's not news, it just happens and no one understands it. The software hasn't crashed. We just don't really understand what the software has done, right? And I think Rob Pike and Brian Kernighan describe debugging in their book, Practice of Programming, and they say it's about reasoning backwards, but they also describe it as being like solving a murder mystery, right? And you're trying to understand, the impossible has occurred, the only information is actually it really did occur, and you need to think backwards to figure out what's happened. And I think the metaphor I often give is the tools we have most commonly use now are if you stick with that metaphor, it's like a photograph of the crime scene with like a dead body on the floor and like a smashed vase or something, and then you have to figure out what happened. And what you want is CCTV, right? What you want is that recording so you can see precisely what happened. Now it's software, so 25 frames a second is not going to cut it, right? You need to be able to see precisely what's happened. But then that's very valuable, right? So you can get rid of all that guesswork and all that trial and error that's inherent in understanding why software's gone wrong. And it's actually, I think it's important for several reasons. The most obvious, I think, is developer productivity, right? And software developers are expensive and they're hard to find, and any software organization that can make them more productive, there's got to be a win, right? But I think at least as important as that is being able to quickly recover from when things are going wrong, and be able to turn around, get fixes out quickly and get things up and running properly. And probably even more important than that is the impact on code quality, right? Fixing those issues that don't otherwise get fixed. And we're seeing a lot of stuff now in a lot of our customers are using it in kind of CI, continuous integration environment inside their Jenkins or whatever. And it's kind of valuable there because the promise of CI is that you get a failure, the CI system will automatically say, hey, it's this commit that caused this test to start failing, so go and fix that commit. And that's really cool, right? What's not to like? Very valuable. Well, at least it's very valuable in most cases, let's say 75%. But in the other cases, the information it's not obvious from the commit why that went wrong. Yeah.
Did you expand the acronym CI?
Sorry, continuous integration. So Jenkins and these kind of things. So you commit some code, it goes off in the background, runs a whole bunch of tests on it, and says these tests failed. Or it's just running. And if a test starts failing, it might do a bisect of the revision control to say this test started failing due to this commit having been added. So you might not run all the tests on every commit, but the system will automatically point the finger at the bad commit. And that's often very useful, but it doesn't help in every case. But what our customers are doing is putting this recording information inside that CI environment so that they get, rather than what you would normally get, which is, this is the bad commit, or at least a suspect commit. Here's some logs, maybe like a core file if you're lucky. But what they also add is, and here's a recording of the failure. So now I can just step that back and forward and see precisely what happened. And it means now I can fix the issues that otherwise don't get fixed. And every customer that I talk to, they all have the same, that there's this set of, we do way more testing than we used to do. And this is a good thing, right? Test-driven development, CI, testing in the cloud, all that stuff we do. I reckon a typical software project today is likely to be doing 2 or 3 orders of magnitude more testing than the same kind of project would have done 10 years ago, right? And that's really valuable. That's a good thing. But even if you have a very low failure rate, and if the tests never fail, then they don't really have any value. So even if you have a very low failure rate, that's a lot of failures to analyze and to triage. And what happens is you get this, in nearly every software project, you get this increasing, I spoke to one customer who said this doesn't happen to them. You get this slowly increasing set of test failures that no one understands why they fail, right? And it's we'll come back and look at that because this week's unusually busy and next week will be better, right? And of course, never is. And so you just get this growing technical debt. And I think part of the reason for that is actually we all know that in practice, let's say 9 out of 10 of those test failures don't really matter, right? Because they're a bug in the test itself, a problem with the infrastructure, it's some really esoteric combination of circumstances. But the others, that 1 in 10, that's like your future security breach or production outage, waiting to happen, right? But how do you know? You can't know which of the failures are the ones that matter unless you analyze and understand all of them. So a bunch of different use cases, but I think probably most interesting is improving the quality of software and especially as we become ever more dependent on it for our livelihoods and increasingly for our lives. So actually, before I get to that, I'm going to switch now to a quick demo to show this stuff in action. So what we've created is it's a Linux technology, records the execution of a Linux process in a way that then can be rewound and replayed so you can see precisely what happened. And I know you guys have sort of similar stuff internally with RDMA and stuff, so you may have seen some of this stuff before, but at least this is how I pitch it to customers, and that might be helpful. So right, so here I have, this is my demo bug program, right? It's a very simple program, tiny bit of C. I'm showing this in Eclipse, by the way. You don't have to use Eclipse. We work with a bunch of different debuggers. One of the debuggers we work with is GDB. So in effect, you can use it anywhere you would use GDB, and Eclipse is just one. Anyway, so here's my really, really simple program. It's got what it does is stores numbers and their square roots in a cache. So the cache is just an array of these structures that map numbers to square roots, 100 elements in the cache, and cache calculate is the function that we care about, right? Which, given an operand, will return the square root, which it does by just looping through the cache, linear search, right? Nothing fancy. Find a match, return the square root, right? Dead simple. Or miss the cache, and then we'll populate the cache lazily, and we'll put one entry either side on the basis there's some kind of locality of reference, and then we'll return the square root. And the main function is just like a unit test, right? Randomized unit test, seeds the random, it loops forever, it gets random numbers here, and then feeds them into cache calculate and asserts that what is returned really is the square root, right? Pretty simple stuff. And I'm going to run that in the debugger. So here we are with the top of main, we're ready to go. And press play. And, oh, sorry, I left a breakpoint set from last time. Let's clear that out. Okay, and continue. And it's crashed. Now, this demo is supposed to crash. So here we are, we've got on the top left here, you can see the backtrace, right? I think backtrace is one of the things that developers probably spend most of their time in debuggers looking at least the good ones. Because when things go wrong, the question is, how did that happen? How did I get here? And the backtrace is a pretty good clue to that, right? It's kind of a guess that the debugger does based on what's in memory and what's in registers, but it's usually good enough, or at least obviously wrong. Now I'm inside the C library here, right? I can see that I've called some sort of assert fail, and I've ended up deep in the guts of the C library, so there's no debug information here, but that's okay, we've kind of followed that through. And I can do what I would usually do in a debugger, which is to look up the call stack. Let's go into my own code where I do have debug information, and now I can start to piece this together, right? So, okay, we've called assert 0. Why have we done that? Well, I can see here that actually I passed in number to cache calculate, and it returns square root cached. If I look here, I can see I had passed in 255, and it returned 0. Obviously, 0 is not the square root of 255. So cache calculate appears to have done the wrong thing. And so, as always, when trying to debug programs, you're thinking, well, why did that happen? And here, traditional technologies kind of run out of steam, right? They just can't tell me. The information of what cache calculate did is gone, right? It doesn't physically exist in the universe anymore. So what I can do here is somewhat better than that. And if I hit this button here, which is the uncall button, it's kind of like popping up the call stack. But actually, it's not a guess. We've really been here. It's rewinding all the state, all the globals and everything else go back to what they were. And now I can hit this button here to just step back in time, right? So I'm going to go back a line, back a line, back a line. Now I've got to here. So now I've got back in time to immediately after cache calculate returned. So the next thing I'm going to do is reverse step into to find out why it did what it did. And I can see, okay, here we are returning from the cache, returning the ith entry in the cache. So this is kind of looking like it's going to be one of those nasty bugs. I, in this case, is 4. Let's have a look at that. Looks like my cache contains bad state. Let me confirm that. And yeah, the 4th entry in the cache tells me that the square root of 255 is 0. So classic kind of data corruption bug. Data structure contains bad data, and again, I'm thinking, how did that happen, right? And who knows, right? It could be another thread, it could be a pointer error, it could be a logic error. Somehow that ended up with bad data, and I need to figure that out. But what I can do here is add a watchpoint, right? Watchpoint, sometimes called a data breakpoint. Very useful feature and exists in most modern debuggers, and what it lets you do is run the program until the data changes. Of course, what I'm going to do is run it backwards until the data changes, right? So it's going to take me back in time to the line of code that most recently updated my data structure. So let me do that. So I just hit this backwards button here. So we've wound the clock back. We've gone back to when the data structure contained good data. The square root of 154 with integers really is 12. And actually, I can step forwards now. And this is like sort of watching action replay, watching sports on the TV, right, as I step this forward. So just watch the data up on the right here, top right, as I step forwards. Step, step. So that's it, right? That's the corruption happening right there. That's the smoking gun. Again, though, it's, well, why did that happen? Well, let's take a look at what's going on. I'm going to look at my local variables here. So we're writing operand adjacent and square root adjacent into the cache, and operand adjacent is -1. So its square root is garbage because you can't take the square root of -1. Well, why did that happen? Actually, right, okay, at this point, we're getting pretty close, and I could probably do it with code inspection, but this is a demo, so let's just keep going. So I'm going to add another watch point to that, and I'm going to go back, and okay, it's being set here. So operand adjacent is being set to operand -1, and operand is 0, right? So here's my bug. Call the function with an operand of 0. It returned the right thing. It returned 0, but as a side effect, it left one element of my data structure in a bad state, and I didn't notice for some time later. Now, this obviously is a trivial little example, and you could probably just stare at the code for a little while and figure it out. That said, it's still not that simple, because like every time it runs, it's going to do a different thing. We'll see the random at the beginning. So how would you do that with a normal debugging? You can't really use breakpoints and try and run it again, because that won't help. And I can actually look here. I can see I've been round. If I go up to my main function here, if I look at I've been around that loop 806 times, and I happen to know that every time I run this, it changes. So it's it'd be hard to track that down. But actually, this is a condensed demo based on a real-world case study. This is all public information. You can download this from our website. That we did with Cadence, right? The guys who do the chip design software. Big, complex programs, millions of lines of code, very long run times. They had a problem with their software at one of their major customers so the customer's doing this chip design, right? So they're running loads of simulations because you want to test the hell out of the chip before you tape it out, because first one costs millions of dollars and second and third ones cost pennies each. And so, lots of testing of the design running inside this simulator, the Cadence simulator, and after 8 hours of execution, about one run in 300, the simulator would just explode, right? Seg fault. And it was a very important customer, so Cadence had engineers on site with that customer for 3 months trying to figure out what was going wrong, because it meant the customer couldn't take their chip out because they couldn't run all their tests, right? It's a big problem. And they found, there'd just be a core file, and they'd look at the core file, and there's a -1 where there should be a pointer, but it's always in a different place, and there's just nothing to go on. So they ran it inside our stuff, right? Now, remember, it only failed one run in 300, so they had to run it a whole bunch of times, but they just did that in one weekend in parallel, set up a little compute farm and just ran the thing again and again. Took a little longer, right? There's a slowdown, so I think that case, rather than taking 8 hours, took about 20. But again, that's fine. They just left it running in this compute farm. And came in on Monday morning, had hit the crash in one of the runs. They were able to put a watch point on that -1, just like I did in the demo, run backwards. I think it took 3 hours to run backwards because the actual corruption had happened a long time in the past. But nonetheless, they did that, and they had it then fixed a couple of hours after that. So they went from 3 months, actually infinite time, because they weren't fixing it, to having it fixed in a matter of hours, right? With big, complex software. So it's a nice example of this stuff does work in practice at scale in the real world. Now today, Cadence has our live recorder product, which is kind of the same underlying recording technology, but as a library that you can link against your code. And that's linked into their product now that ships out to customers. And now when they get those kind of problems, they can just say, turn on the recording, generates a recording file, send that back to Cadence. Cadence engineers can load it up into that or something like that and just see what happened, right? And debug what happened. So that's very quick sort of product demo, if you will. I'm going to talk a little bit about state of the art, a bit about how we've implemented this, and we'll just sort of see how far we get. But any questions at this point before I go on? Yeah.
This live recording, what's the overhead?
So it varies depending on the program, but it's typically half speed, can be better, can be worse. It can be up to 5x, maybe more slowdown.
So your customers are running it continuously?
No,
Okay.
not well.
So how do they?
One or two do, but most don't, because that amount of overhead is sort of intolerable for always on. But it's when you've got a problem and a thing that's failing, if you then turn on recording on that. So there's two things. One, you don't have to record the whole program. You can start and stop recording the bits you're interested in. And the other one is, you've got a problem. Customer phones up and says, well, when I do this, it crashes. So okay, we'll do it again, but now we're recording.
I see. So they tell the customer to turn it on then.
That's one use model, yeah.
It's deterministic, which is a big problem in these cases, right?
Right. So in that Cadence example, I just have to do it a whole bunch of times until it fails. Now it depends, right? So that's one use case. That's in the kind of the classic ISV. You're shipping software to a customer and it's failing on site. Increasingly, of course, these days software's running like in the cloud or some kind of service. And you've got a bunch of nodes. So you can turn on recording on one of your instances. Wait for that bad thing to happen, right? So, but I think it's certainly a kind of an always-on recording would certainly be very valuable. But I think you'd have to see a better level of performance than we currently offer to make that practical in the general purpose. We do have cases where people have done that, low CPU overhead programs that crash very occasionally, just turn it on and wait for it to crash. But yeah. Okay.
What's your replay overhead?
It's comparable to the record overhead. When you're replaying forward, actually, it's often quicker to replay forward because all the I/O is kind of stubbed out. If you sleep for 10 seconds, that will be instantaneous when you're replaying. Going backwards is often a bit slower. We've actually got some changes in that we haven't released yet that will mean that the reverse operation is actually comparable in speed to the forward operation. Right now in the product, it's a bit slower. So let me, yeah.
How multi-threaded are these programs in general? Like, what's a good target for you?
Some of them are really quite multi-threaded, actually. But yeah, so let me talk a bit about the way that we've implemented this, and then we'll come back to threads and how that works. So I'm going to actually switch to another view here, just a second, while I just make this work. Just 1 second. Where's it gone? Oh, sorry. Here we go. So I've got some kind of crude ASCII art to just sort of demonstrate this, but we'll make it pretty one day. But anyway, right, so let me drag that across. All right. So yeah, so actually, let's talk about how we've implemented this. This fundamentally is hard because every time you write a value to memory or to a register, the state of that is gone, right? The information has been destroyed. I know there's some interesting work being done here to kind of reconstruct some of that, but in the general state, in the general sense, general case, it's gone. So you need to be able to reconstruct it. So there are different ways to try to do this. One is that like every instruction that executes, you just sort of look at you diff, you see what that instruction changed, or maybe you see what it fetched from memory, and you store that in a log so that you can replay it or reconstruct it. But that has a problem. One, it depends how you do it. You can make it quite quick, but it's still going to be probably slower than we would like, and it does tend to generate a lot of data, right? So billions of instructions every second. If every time you read from memory you're recording what you read, then that gets pretty heavyweight. So we actually use a re-execution approach, right? So we're exploiting the natural determinism of computers. If you run a program multiple times and every time you do it, you have the same starting state and you feed it the same set of inputs, then it will do the same thing. Which is why random numbers are difficult to generate, right? And we can exploit that, which we do. So we kind of snapshot and re-execute. So as the program's playing the first time, we take this snapshot. Now, this is all built on Linux, so we can kind of cheat and make our snapshots based on fork, which is really handy because it's all copy on write, and it just stores exactly what we want it to store. But anyway, so we take a snapshot at the beginning, and we're recording the program. This is what we call in record mode, right? And then let's say it opens a file. Right, that's a non-deterministic event. Next time you play that, maybe the file doesn't exist anymore, right? Or whatever. So we store the result of that open. Carries on executing, maybe it reads from the file. Very likely to be non-deterministic. May not be. Actually, we do have a way to tell you can guarantee to say, actually, this file isn't going to change, so don't bother storing the results. But by default, we'll store the results in our event log. Keep going. We take another snapshot, just because like we decided to. It's an optimization. You don't have to take multiple snapshots, but obviously it improves the performance of replay. So then we do a write, take a snapshot, another write, that goes in our event log. Okay, so you can see we've got this kind of, these snapshots. Now snapshots are just an optimization, like I say, we wouldn't actually need them. But now let's say we're going to go back in time, we're going to play back. So what we do is actually we take a snapshot and we play it forward, right? And we'll search the history space. So we're looking for, let's say, a certain time that, we're stepping back to a certain time, a particular program counter or some other search criteria. So we'll take that snapshot and we'll play it. If we don't find it, we'll take that snapshot and we'll play it. And so, okay, so we go, let's say we're going, so we go back, actually we would go back one snapshot at a time, but anyway, we've gone back in that point. Now we're playing it forward. We can create another snapshot in replay mode if we want, and we can create and destroy snapshots as we go. And now we play forward, and when we're replaying these snapshots forward, we are not really doing these non-deterministic operations. We're just like reconstructing their effects based on what's in our event log. And we do things like so the snapshots are relatively cheap because they're copy on write, but they're not free. Right, and certainly like programs with large working sets will touch those pages quite frequently, and then you'll build this sort of these copies of pages up inside the system. So we try and keep this number of snapshots low-ish. It's configurable. We actually also dynamically kind of scale them back when we notice that memory is getting a bit tight. But by default, we'll keep between 25 and 35 snapshots in the history. So it's not a huge number. But we we've experimented with various approaches over the years, but we found that actually simple works best, just a kind of uniform separation of snapshots, but keeping one at an interesting point in time. So what's interesting? Well, generally it's where you've stopped. You've hit a breakpoint, or signals come in or something, so we can keep a snapshot there. But the way that we build all of this is on top of this binary instrumentation that we do. So we JIT the machine code, the x86 or the ARM code as it's running, and that allows us to get our fingers in and capture those non-deterministic operations as we need them, right? Now inside a Linux environment, or Unix in general, it's pretty well defined what the non-deterministic stimuli to a process are. So you've got basically system calls, you've got thread switches and thread interactions, which I'll come back to in a minute because there's a question. You've got asynchronous signals like sig-alarm or whatever. Some instructions are non-deterministic. Read the timestamp counter as an example, right? Most instructions, they do the same thing. If you add two numbers together, you get the same result, but hopefully anyway. But read the timestamp counter, and some other things actually turn out to be non-deterministic. And there's accesses to shared memory. That's memory shared with a device or with a kernel or with another process. We're able to catch all of those and store them in our event log so that we can replay all of those programs precisely. So coming back to that threads question, so yeah, the catch with this is multi-threading. So what we do is we kind of cheat, and we do what a lot of these kind of tools do, Valgrind and other things, is we kind of serialize those threads, and we force one thread to execute at a time. We allow the OS to do the scheduling and decide which thread to run when, but we just force one thread to run at a time. And then we can detect those thread switches, and those go into our event log. And then when we replay, we can replay those thread switches precisely. So the kind of ordering is guaranteed. So, but it does mean that your user mode code is running kind of single threaded or single core. I/O and stuff can still be parallel. We find that actually a lot of customers' code is not quite as threaded as they think it is. And so we do have cases where people are using this with a very large number of cores and threads. But there are certainly cases where it is genuinely scalable and you've got some sort of embarrassingly parallel problem and it's distributed over, we have one who has up to 4,096 cores in the same machine, which is just insane. And then the slowdown gets pretty bad, right? Because you're just running one thread at a time.
How significantly is the overhead affected by, the multi-core characteristics?
So it is affected very significantly. So if you had a perfect program that had 2 threads running on 2 cores and it got full parallelism from both those cores, then inside our stuff, that's going to double whatever overhead we'd have for the single threaded case. Yeah.
Basically, the
Yeah.
linear
Yeah.
decrease.
Yeah. Yeah.
So,
But only if, to just kind of slightly caveat that, I mean, it's true in general, but only in the case that those are perfectly parallel, and actually most algorithms are not as parallel as you would like. Exactly. So it's not as bad a problem as one would expect in practice, but it is definitely an issue, right?
sure.
And certainly there are, so workloads that are what you might call lightly threaded are quite good for us.
Understandable.
So do you have a Windows implementation?
We do not.
Okay, and is that because the Windows API is so much more complicated?
On no fork.
And no fork?
Yeah, I mean, I think all these things will be surmountable. Actually, it's kind of always been there as a thing that we'd like to get around to doing. We've found plenty to keep us busy as a company in the Linux world. And I guess we're just kind of, it's that. So there are certainly I think this is technically easier on Linux than it would be on Windows. Yeah, fork is useful. It's I believe, a smaller set of system calls to worry about. You can just kind of look at the source code as well, which helps.
It's an order of magnitude smaller.
Right, so there you go.
It's 300 something over versus 4,500 something.
Yeah, so that's going to be, so it's a big engineering effort to do. Clearly it's a big market, but we're a small company, right? We're 19 people, so there's just a limit to what we can chew. Yeah.
I was just wondering, following just one more question on the concurrency thing. So in your experience, your machinery is good at, if you have a concurrency related bug, a hard to find bug, etc., it's still, even so you do affect the scheduling in a way.
Yeah.
But it's still, in your experience, an effective tool for finding concurrency related bugs, data races, deadlock.
Yeah, for a lot it is. For some it's not, right? So it's preemptively multi-threaded. So if you have just a single core, you can still have race conditions. Actually, turns out that when you we try to perturb the scheduling as little as possible, but clearly we are making quite a big difference to it, right? And it turns out when you're doing that, as you'd expect, you make a lot of unlikely things much less likely or even impossible. So if you've got a race condition where you've got, say, a missing memory barrier between 2 threads, that's just not going to reproduce at all. You'll just not see that. If you've got a missing lock, that may well reproduce. And actually sometimes, and it does, we had a case of this very recently with a big customer of ours, it becomes more likely to expose the race condition because we've just changed things, right? And we've just thrown all the chips in the air, and so some of those very unlikely things can become more likely to reproduce. I think in general, I would say if it does reproduce, it's almost always then really easy to understand and get to the bottom of it. The big thing is, can you reproduce the problem? And I'm always very clear, right? This is a tool, and it does not fix all problems. It does not make programming suddenly completely easy in all cases. And the big thing about whether or not it does is, can you reproduce that bug inside the recording? If you can, it actually almost always is really easy. When you can't, then we can't help you. Yeah.
Any room or any demand for something in the middle between the fully uninstrumented full speed and this, the snail-based kind of version where you, for example, remember your thread decisions,
Yeah.
so that it's easier to repro later on.
We have sort of done some thinking on that and looked at it. I think there could be. It's not anything that we've implemented, but yeah, you can certainly see a case, slightly less than perfect replay,
Yeah.
but you trade off for faster execution. Yeah, definitely. Yeah.
So how do you detect changes, like in the shared memory or even a memory mapped by some device that could be changed at any time in a synchronized way?
We do it really well. Yeah, it's really cool.
Okay.
But I'm not going to get into the details of how we do that because it's kind of a secret. But we have some clever stuff to do that.
Okay.
Yeah. Okay. Let me come back to. So we're not actually the only people to be doing this kind of thing. There's a lot of it in the literature, and there's a lot kind of just more kind of production stuff now, and companies doing this or open source projects or whatever. So on Linux, for Linux native code, this has been in GDB for some time. It's functionally very similar to what we do, but it's a completely different implementation. What they do is to single step every instruction and look at what changes. So it goes very slowly and it produces very large event logs. But it's kind of okay. And if you can stop close to where the problem is, or you've got a small program, then it works pretty well. I think I've heard that the most use that gets. Of course, trouble is if you can stop very close to where the problem is, you're 90% the way of solving it anyway. But where I've heard it is very useful is, this is all really about, it's about code comprehension, right? And that might be because you're trying to debug it, you're trying to understand why it didn't do what you wanted it to do. But it might also be because you're just trying to understand what this bit of code does that someone else wrote. Maybe you wrote a long time ago, but more likely someone else. And particularly where I've heard stories where somebody else has written some code that's very clever, and they've been really smart and removed a couple of lines and saved a few cycles. And it can be quite hard to understand. And stepping through with GDB's reverse debugging capabilities can be quite useful. There's an open source project called RR, which is much closer to what we've done. In terms of that does the snapshot and replay stuff. It's a different implementation. It's based on, they don't have a JIT. They hook into the performance counters on the CPU. So it can actually go faster than we can in record mode. It does have some limitations in terms of the platform support that it can have. So you need to have the right CPUs and the right kernels and things. But if you've got everything in place and you can do it, works. They can't do shared memory. Otherwise, it's kind of quite similar to what we're doing. In the Windows world, that's the Nirvana, RDMA stuff that I know is, there's some papers some time ago, but I believe still used quite a bit internally, which is kind of halfway, I suppose, between what we do and what GDB does. At least as I understand it, anyway. And please correct me if I'm wrong, but it's recording for the most part, the memory loads, which has the nice effect that you can record multiple cores concurrently, but does require a lot more storage in the log than we do. So you're kind of much more limited in how far back in time you can go. There's a thing that's been, as far as I can tell, announced but not released called Time Machine for .NET. I don't know how it's implemented or whether it works or how real it is, but I have seen some stuff about that. And of course, the Chakra core changes which are merged. Is it released yet or merged and not released?
Source
Yeah,
repo,
yeah.
and we've put out a couple of previews for people to code,
Yeah,
but
yeah.
we're getting it.
Yeah. There's a thing on Java called Chronon, which gets some use. That's done at the JVM level. It's quite slow, uses quite a lot of memory. It's not to the extent that GDB does, but it does work, and it's got the nice benefit as well being quite cross-platform. There's a thing called Helic, which is new, kind of like Chronon, but they do some kind of visualization stuff on top. And the most recent thing I've seen is PyPy, the Python project to implement Python in Python. They've built a thing called RevDB they've just announced, which it kind of gives that reversible debugging for Python, which is quite cool. There are almost certainly others that I've missed off the list. Yeah.
Just if you care, you should probably put pin play on your slide.
Okay. Yeah.
It's actually the most, it's multi-threaded, very slow, 100 to 200x. Trace size is significantly smaller than IDNA, or IDNA is already significantly smaller than GDB. And on RR, he cannot do shared memory, MMIO, or some kernel calls. For example, he cannot do async IO.
Yeah.
What's the name of this again?
Sorry?
What's the name of the tool?
Pin play.
Pin play.
Pin play. Okay, got it.
So,
It's from Intel, I said.
yes, pin play from Intel, that one works cross-platform.
So that's cross-platform, right? Yeah.
Pin play is cross-platform.
Yeah. Okay, but I'll add pin play to these slides. I mean, there's quite a long list of research projects as well.
Pin is one of the most used ones.
Yeah. Okay.
It's probably
Worth putting on. Yeah.
In the previous slide, we had 25 to 35% improvement in developer productivity.
Yes.
How did you measure that in which scenarios?
We did that in two ways. It's kind of qualitative data. We did, but a study was done from the Judge Institute at Cambridge University, which is kind of the business school of Cambridge University. And what they did is basically polled a bunch of people who were using our stuff and anything vaguely similar they could find, it's mainly our customers to be honest, and just said, what productivity do you see? What productivity wins? And what came back is, well, we spend on average about half of our time debugging, and we were including in that, like, just because it doesn't work first time kind of debugging, not just there's been some report from a user, and on average it came back that we can debug in half the time with this stuff than without.
So what about interviews and, I don't know, any experiences that emerge there, right? Even from, I don't know, you talk to 10 people, you have them do a task for an hour, you interview them afterwards. You get, the top, sort of the cream of their experience, right, is not so difficult to get. Some of the fine-grained details take a while.
Yeah. That would be really interesting to do something like that.
What are the remaining frustrations? Maybe that's a different question to ask.
Right. Yeah. So, I think the two are performance and reproducibility. As the faster you can make the recording, and the smaller the logs. But some people care about the size of logs. Embedded devices don't have a lot of memory, that kind of thing. But mostly it's about the speed of the recording. And then being able to reproduce all the time. One of the things that's kind of frustrating, actually, going back to a previous comment about how likely it is to reproduce race conditions, we have had several times customers say, well, your stuff's broken because I run my code normally and it works, and I run my code under your stuff and it fails, and it fails in a way that isn't the bug that I'm looking for. Now, sometimes that is our fault because we've messed something up, but not always. Sometimes it is a genuine bug. Yeah.
In terms of customer use cases, do you find it's mostly for like debugging some kind of an issue that's already manifested, or do some people use it for like general like instrumentation to understand the characteristics of how things are run in production or things like that?
It's today, at least, it's much more just investigating those issues that have come up. Either it's like I'm writing some code and it's not working, customer bug, or something in test. But rather than just sort of the general kind of characteristics. Now, clearly, there's very interesting things you can do, right? And when you have this style of recording, where you have everything, you can start to do some really interesting analyses on top of that. I think there's a huge amount of research and even product development I'd hope that we do at some point. But today, we don't really have that. The only time where it is used outside that kind of debugging thing, as I mentioned earlier, is just trying to understand how code works. And it's actually really useful for understanding a foreign, complex code base. And they tend to, things get tangled up, and you're stepping through, and you don't understand. What you get lost if you're stepping through in a regular debugger in someone else's big code base. It's very easy to just get lost, and it's like, oh, I've gone into some weeds I don't care about, and now just be able to go back to where you were is really valuable. But that's kind of the only case. It's not just debugging today.
So is containing side effects a significant issue in your experience with the customers? By which I mean, if you have a program that shoots missiles, then record replay is probably not such a great idea, right? That sort of thing.
Can you elaborate?
Well, so if you have programs that talk to external systems, right, to send things up to the cloud, right, to databases, burn DVDs, shoot missiles, as I forget that earlier, then, this whole business of side effect and what to hold back and what not to becomes more challenging.
I see. Yeah. Well, but not really. It's not really challenging because if it's an external side effect, then we hold it back, right? So it's at least in the current implementation. Now, in the previous suggestion, well, maybe there'd be a halfway house. It gets more challenging.
Are you always able to tell precisely what it is?
Yeah. Yeah.
Because it any false positive side effects?
Well, we sometimes record things in the event log that we don't strictly need to. There's an optimization. We could take some stuff out. But yeah, because it's pretty well defined, right? You've got, because the process model. On a protected, it's an inherent thing to a protected OS. This is my process, and I define carefully the ways that somebody else can affect me. Like I make a system call, or I share some memory with somebody, or something like that. And if somebody else can affect me in a way that isn't through some memory that I've shared or a system call that I've made, then that's a pretty serious security vulnerability in the OS, right?
So how big are your log files? Like for an 8-hour run, how much? How big are they?
So, yeah, I mean it varies because of the technique that we use of this snapshot and replay. Now, just storing the non-deterministic stimuli, it does vary enormously. So this isn't like a politician's diversion from the answer. So the example I gave of that Cadence run, 8-hour run, I think they had a gigabyte log file, and that was enough to store everything. But that was an EDA tool doing a simulation run. So there wasn't a whole amount, not a huge amount of external stimuli. Like it reads in the design at the beginning and it does some stuff, and then it's just computation. It's just crunching through the numbers. So we don't actually need to store that much stuff. If you're reading like uncompressed high definition video off a socket, then we're gonna store a lot. But we do a kind of circular, it's a circular buffer. So you just choose how big you want to make it. And then, if you need more stuff than that, it goes off the back. And then it does mean, of course, you can't go back in time before that. But, that's pays your money, you takes your choice. And of course, there's a snapshots as well. But they're just an optimization. So we kind of, when we're getting short on memory, we prune them away.
I was just wondering, so today most of your customers, they use this machinery for in-house testing, like you were talking about the CI scenario at the beginning, or post-mortem, I have this bug deployed already, basically, and I'm trying to figure out what the hell is going on there. The latter or the former? Or
it's certainly both. I think we're seeing a shift over time to become more actually internal testing stuff. And I think that's partly because, as I said before, that there's this sort of cultural shift in software development underway at the moment with continuous integration and even continuous deployment and DevOps and all this stuff. So like we were down at, one of the reasons I'm on this side of the pond right now is we were in Jenkins World Conference last week, where we were showing this plugin that we've made to sort of integrate with Jenkins and allow that stuff to happen, and it's valuable there for sure. And the more people are doing that, I also observed, and I kind of touched on this in the intro, when we started. So we didn't find this whole kind of CI use case. It found us, if you like. We just found that several of our customers were all doing the same thing, and most of them were using Jenkins. So we sort of thought, well, rather than all of our customers independently lashing it together, maybe we'll just make a plugin and provide that. And what I found was that talking to people about this stuff, once we realized that actually there's something here, it depended where they were on that journey down the continuous integration thing. So if they were like right at the beginning, you know, if I was talking to somebody who's in the process of deploying Jenkins or whatever CI, and I said, wouldn't you like it if you can record those test failures so you can go back and see them? They were like, not really that interested, because they were sort of thinking, well, CI is going to solve all my problems, right? And it's just going to give me the check-in that caused a problem, and then, you know, I don't see the value. Those who'd been using it for some time were aware of, you know, the limitations and how you just kind of, and it's always the way in technology, right? You have something that solves a problem and works really well, which it does. And it's like hanging wallpaper, and you squeeze out this bubble, and then this other bubble appears somewhere else, right? And you kind of, you just move the bottleneck. So yeah, I mean, I think I couldn't give you a percentage, but I'd say the majority now is in-house, but not a big majority, right? And there's still a lot of external stuff, because the stuff with the runtime, particularly when you're on ISV shipping code, you really lack visibility, right? And we've all been there of you know, some sort of customer complaint doesn't work, and you say, well, I'm doing X, Y, Z, and you say, well, I've done the steps you said and it works for me, and those kind of things are really hard to solve. But you know, then there are other issues, right? Getting the data back can be problematic. They can, you know, because you know, like these recordings contain, like the good news is they contain everything that the program has done. The bad news is that they contain everything that the program has done, and you can have passwords in there, or you know, other kind of sensitive stuff. So that can be a challenge.
Windows has a similar technology to fork called process snapshotting that uses copy on write but doesn't execute code in the target of the fork. And we've used that in a couple of production scenarios, and customers have talked to us a little bit about a concern about an increase in page faults, which is completely variable on how many writes how many pages the actual original app continues to write to.
Yes.
Have you seen in practice that that's been a problem, especially in your production environments, or our data has shown that really for normal locale it's not really an issue, but
yeah, it's actually it's been better than I might have thought, actually. So I mean, so what you know, sort of business side of things, but we identified what they call a beachhead of the EDA industry, right? The Cadence Synopsys mentor of the world. That was a good target audience for us when we started, because it's kind of big enough industry that there's some money there, but not so big that we just kind of get lost, right? So that was kind of our beachhead, and it had some good technology fits, right? A lot of it's single-threaded or lightly threaded. It's running on Linux. It's all C++ code. But the bad thing about it, from our point of view, is what they all do, whether they're synthesis tools or simulators. You've got this big design of this chip, and the simulator just goes through and it clocks every gate in the design, and then there's a new clock cycle, and it comes around and it does it again, right? So it's like pathological in that case, very big footprint, and it's just touching all of the pages in one big loop. And so that will generate page faults and those copy on write faults all the time. And actually in practice it's okay. So yeah.
All right, so I think we're getting close to an hour here, and we kind of moved into discussion. So it might be good if you have any sort of concluding slides or remarks you want to make, and then people they're getting hungry, they can go get a little early lunch, and anybody's interested, we can stay for the discussion part. So.
I think, let me just check what's in, we've probably covered all of this. CI we've talked about, customers, live recorder, this stuff we've talked about. I think we've covered all the main stuff. Yeah. So I mean, an interactive discussion is always good, right?
All right, excellent. I didn't want to cut off the discussion.
Yeah.
Please feel free to continue asking questions.
That's what happens,
Some people get hungry.
Sorry, you asked for discussion.